people tend to have heard of metallurgy as a discipline. So people say they know about metallurgy, and that really is the study of metals, and that's the kind of foundations from which the discipline of materials science was built. But we realized that in terms of engineering the devices that we need in the world today, we need a lot of materials that aren't metals. So material scientists think about all materials we might use in engineering, not just those metallic materials. But if we look at the sorts of things that material scientists, metallurgists traditionally did, they looked at the properties of materials and compared them to their structures. So the classic sort of thing a material scientist might do is look at how strong a metal is and how it deforms when you apply a force to it. So what I've got just here, let me get a pointer, is a stress displacement curve telling us what happens to the shape of a copper sample, how it extends when you apply a force. And there's different samples that have been processed in different ways, and how we treat or process or fabricate materials to get them to have the properties we want is a big part of materials science. And the properties of the copper here are being controlled by its small scale structure. All crystalline materials contain defects, mistakes in the perfect crystal structure. And this transmission electron microscope is showing up some of those defects which are called dislocations, and which are responsible for this kind of stress strain behavior that we see in metals. They're responsible for controlling at what point a metal starts to deform permanently when you stretch it and get stretched and pulled out of shape. So a dislocation, and these are going to be quite important defects, crystal defects in this talk, is a line defect through the material. And I've got a kind of illustration of one here, and you're looking here like down the end of the line defect. So you can imagine this defect extending into the screen away from my pointer, perpendicular to the plane of the screen. But in the perfect crystal, what we'd have would be lines of atoms, or in fact, planes of atoms extending into the screen, which are all beautifully ordered and not distorted. But when we get across to this defect, we can see these planes of atoms starting to bend. And then here, there is a missing half plane. So just here, this plane stops in the crystal. It ends and other planes continue on past it. It's like inserting an extra piece of paper between the pages of a book that only goes halfway in and kind of bends the pages around it. And all along the line, which is the edge of that half plane extending into the board, the bonding in the crystal is now no longer complete. The atomic bonds around this, the atom here, and similar atoms that extend into the plane of the page are no longer all meeting up in the way you'd expect them to in the perfect crystal. So that's a key defect that controls the mechanical properties of copper. But how does that link to LEDs? And why do material scientists care about LEDs, light emitting diodes, anyway? Well, my argument would be that everybody should care about light emitting diodes, because these are really energy efficient sources of light. Compared to the kind of conventional light bulbs based on flowing a high electric current through a wire and having it get so hot that light is given out, the energy efficient light emitting diode technology could save 1.4 billion tons of carbon dioxide every year. And it can avoid the construction of huge numbers of power stations fueled with fossil fuels. So this is a technology that really has the potential to improve the sustainability, or how environmentally friendly lighting up our homes and workplaces are. So those LED bulbs that some of you might have at home, or that you might know about being installed to reduce electricity consumption in different buildings, well, what's inside them? They look like a conventional light bulb, but if we remove this kind of plastic bowl on the top, underneath there's something which looks a bit like a table tennis ball, a yellow table tennis ball. And it's actually an intrinsic part of how the LED works. It's a phosphor, and a phosphor here is designed to take in light at one color and emit light of another. If we lift up that phosphor cap, we see underneath the actual PCB with the LEDs on. And this particular light bulb has several LEDs in it. Now, if we go in depth a little further, then we can get into the actual semiconductor structure of the LED. It's based obviously on a PN junction. And if we zoom in on that PN junction, we can see here in transmission electron microscopy, the detailed structure of the light emitting region. Specifically, the region I have here labeled as MQW, these are multiple quantum wells. Zooming in further, those quantum wells consist of very thin layers of indium gallium nitride. In this example, layers 2.6 nanometers thick, separated by barriers of gallium nitride, here 5 nanometers thick. So it's still difficult to see the link, perhaps, between my copper that the metallurgists were interested in and these LEDs. So where is the link? Why did I introduce these defects, these dislocations? Well, because unfortunately, gallium nitride materials have huge densities of these dislocations compared to other semiconductor materials. This is a transmission electron microscopy image of gallium nitride, and we're looking at the material in atomic resolution. So each of these bright dots is a column of gallium atoms extending into the page, not actually a single atom, but nonetheless, we're seeing here the atomic structure. And you may be able to see that there's something odd going on over here. And if I draw in the positions of the planes of atoms running through the gallium nitride crystal, what we find is this dislocation structure that I illustrated earlier, a half plane of atoms that stops in the crystal, with the other planes of atoms bending around it and distorting the local crystal structure and the atomic bonding. This is just the same type of image, but now with a very, very detailed look at the atoms around the dislocation core and a simulation here of that slightly noisy transmission electron microscopy image, which is based on a structure here, kind of a ball and stick atomic model, if you like, of the dislocation. And we can now see that there's different numbers of bonds around the atoms in the normal crystal compared to the atoms in this crystal. We're no longer forming these 6-membered rings, but instead the bonding has been distorted to form here a 5-membered ring and here a 7-membered ring. So a different bonding structure and a real disruption in the periodicity of the crystal. This is now a more zoomed out transmission electron microscopy image, looking at a light emitting diode, a very simple light emitting diode in cross section. And we've got P-type gallium nitride at the top, N-type gallium nitride at the bottom, and in between the quantum wells. But running through now, we can see these dislocations as lines. So in the previous images, we were looking like down the end of the dislocation line and the line was into the page. Here, we're looking at the actual lines themselves from the side, and we can see they come up all the way through the device. They're arising because gallium nitride is typically grown on crystals like sapphire or other substrates that are not the same material. They are unlike substrates with different spacings of the atoms in that substrate. And that's the fundamental cause of all these defects, is this what we call heteroepitaxial growth, growing an unlike material on a substrate. And it causes all these mistakes or dislocations in the crystal. Now, that's kind of remarkable because gallium nitride in a typical LED has a density of those dislocations in a unit of per centimeter squared of about 1 billion defects per centimeter squared. Sometimes we get down to only 100 million defects per centimeter squared, but really, really huge numbers of defects. If we look at a material like gallium arsenide, which is the material used to make red LEDs, well, actually it's used to make infrared LEDs, but it's a traditional LED material. the density of dislocations is only about 1,000 per centimeter squared, whereas gallium nitride, which is used to make the blue LED, there the dislocation density is orders of magnitude higher. Now we need the blue LED because it's the blue LED emitting the high energy blue light to shine upon that phosphor cap, which is then going to convert it into other colors. That process is what is going to give us white light emission, okay? So we really, really do need our blue LEDs, but they have this huge density of defects. And the remarkable thing is that these devices are very long-lived. Their time to failure is in excess of 50,000 hours. Now, if we were to take our gallium arsenide-based devices and increase the dislocation density by about an order of magnitude, so not up to this 1 billion per centimeter squared level, but just up to say 10,000 per centimeter squared, then the time for failure for those devices reduces from maybe 50,000 hours, 100,000 hours, down to less than 100 hours. And if you were to increase this defect density still further in your classic gallium arsenide semiconductor material, you'd expect the device to fail almost as soon as you switched it on. These devices cannot tolerate this very, very high density of defects. And when gallium nitride was first synthesized for LEDs, people assumed that it would never work because the defect density was too high. The crystals were simply not perfect enough. So let's think about what's going on inside an LED. We've got these indium gallium nitride quantum wells, and we're going to inject holes from the p-type gallium nitride, electrons from the n-type gallium nitride, and they're both going to be trapped in the indium gallium nitride quantum well, where they will recombine, and that's what's going to give us light emission. So the role of the indium gallium nitride quantum wells is to trap the carriers together in a really small volume. That means that because they're trapped together in the same small space, they're much more likely to meet and recombine. So that's the role of the quantum well. It also defines by its composition and thickness what the wavelength of the emission is going to be. But the key thing is getting the electron and hole together and increasing the rate of their recombination. It's a bit like if I were to say to you, oh, come over to Cambridge and we'll meet. It wouldn't be much use if I just said, let's meet in Cambridge. You might never find me. But if I said, come over to Cambridge and we'll meet, and I'll meet you in the material science department in the reception area, well, that is a nice confined location, and it's very likely we would find each other and manage to have our meeting. So it's all to do with trapping the electron and hole together in this small space. Now, that's all great. We've got our indium gallium nitride quantum wells. They're tending to recombine and give us out light. What happens when we introduce our dislocation, our defect? Well, if we look at this band structure that I'm drawing here, the dislocation, the defect, which is running all the way through both the indium gallium nitride quantum wells and the gallium nitride barriers, it's going to introduce extra states in the band gap. And those extra states are going to provide a different route for the electron and hole to recombine. The electron can essentially trickle down via these mid-gap states, which are generated because of that break to the periodicity which the dislocation is causing. And that's going to mean that instead of emitting light of the wavelength we desire from this LED, we're going to be giving out heat. And what we'd expect is that the more dislocations we put in, the more heat is generated, and that heat in various different ways damages the device and causes it to fail. That's certainly what we see in materials like gallium arsenide. But in indium gallium nitride, that doesn't seem to happen. I'm looking at my quantum wells now kind of as a semiconductor sandwich. The quantum well, the indium gallium nitride layer here, shown in orange, is like the filling in the sandwich, and the electron and hole are confined to that sandwich filling. If I introduce a defect, a dislocation, because it cuts through the quantum well, through the sandwich filling, we'd expect the electron and hole to be able to move around within this layer and get to the dislocation and for heat to be given out. There's nothing stopping the electron and hole moving in the plane of the quantum well in our kind of classical picture of a quantum well. The electron and hole can't necessarily easily get out of the quantum well, but they can move around in this 2D layer. So there must be something, people postulated, that stops the electron and hole from being able to move around in the plane of the quantum well. And one of the concepts that was suggested when these LEDs were first made was that the indium content within the quantum well was varying, and that there were blobs, regions of high indium content, and that those regions of high indium content were local regions of lower band gap, and that lower band gap material could trap the electron and hole. So this electron and hole are trapped in a little local low band gap splodge, and they're going to recombine right there and give out light, and they're trapped in such a way that they can't move and diffuse and reach the defect. So that was one possibility. The other thing is that we know that in a quantum well, the confinement energies are very much dependent on the width of the quantum well. And here, where we've got a thick quantum well, the confinement energies will be lower. That means the energy of the electron and hole trapped in the thick region will be lower. And hence, again, we expect the electron hole to get stuck at the thick bit of the quantum well and not able to get to the defect, because they'd have to escape into the thin bit of the quantum well, and there'd be an energy barrier to overcome. So those were some hypotheses about the structure of the material. And now, talking about this way that the structure might link to the properties of the material, how it emits light, we're really getting to the heart of why this is an interesting material science problem. So what is a material scientist? I still haven't answered my own question. Well, a material scientist studies the properties and structure of the material and how they link to the performance of that material in the applications we're interested in. And we try to control both the structure and the properties by changing the processing, the fabrication, the way we make the material. Okay, this is something called the Milton-Fleming tetrahedron of material science, and I feel it's a really kind of excellent, simple expression of my discipline. Now, in the problem we're thinking about here in our LEDs, we've been looking at what the structure might be in order to control what the structure of the quantum wells might be in order to control the motion of the carriers and therefore have the property of efficient light emission. One of the things that we want to be able to do is know the structure, know what a good structure looks like, so that we can alter our processing to promote that structure to get even better LEDs, better performance. Okay. And actually, all the way back in 1997, a group of people in a paper led by Naokawa in APL thought they'd found the answer. They took this transmission electron microscopy image of some indium gallium nitride quantum wells. And we can see that the quantum wells look all blotchy. Now, in this image, actually, the contrast is arising from strain. Okay, that's the contrast mechanism in this sort of TEM. The suggestion was that regions of higher indium content would cause higher strain, so that this blotchiness corresponded to this variation in indium content that had been postulated to trap the carriers and keep them away from the defects. Now, that was all a great idea, but there was a problem with it. So everyone thought, aha, we've got these big indium-rich regions, these splodges of high indium content material in the quantum wells. That's how the devices work. Then people started taking some more detailed pictures of the quantum wells. This is a high-resolution transmission electron microscopy image of some indium gallium nitride quantum wells. The lines you can see running across, I hope, there's thick dark bands, which are the individual quantum wells, and then there's these very thin lines, which are the atomic planes in the nitride crystal. And we can see this crystal these quantum wells are a little bit blotchy, but not anything like as much as we saw in the last slide. Now, what I need to do here is start an animation, and then I'm going to have to briefly switch over the sharing so that you can see the thing I'm trying to play. Okay, give me 1 second. I'm going to stop sharing just for a second and share a different screen. Okay, now what I'm showing here, which I hope you can see okay, is a video of what happens to those quantum wells if we keep on imaging them in the TEM. So this is just, the time is speeded up, but basically we're just taking sequential images in the TEM. And this is what is going to occur. So I'm just going to play the video now. I hope you can see it. And we can see the contrast changing in the image. Okay, I'll just play that again. So we can see that the quantum wells that were not very splotchy develop more and more of this splotchy strain contrast. And that became a big concern because although we had assumed that the electron microscopy images were showing us these indium-rich regions, which would be very, very important for how the LED operated, in fact, when we started to look at how the electron microscope affected the LED materials, we saw that it could actually create this contrast, that the contrast wasn't intrinsic to the materials themselves. It was a factor of how we were observing those materials. Right, give me one moment and I'm going to go back into the slides. Okay, so we had this situation where we were trying to understand the formation of these indium-rich regions in indium gallium nitride. And the transmission electron microscopy was starting to give us doubts about whether these were real structures. It might be that there are really large indium-rich regions in the quantum wells, or it might be that they're just produced by the damage created by that electron beam in the transmission electron microscope. So I'm a material scientist. I have friends who are metallurgists. So what would a metallurgist do in this situation? Well, a metallurgist would look at the phase diagram. The phase diagram is something which tells us, for, in this case, a solution, what different regions of material we're expecting to find. So what we've got here is an axis which is in composition from gallium nitride to indium nitride, and we've also got temperature. And this is from a paper by Stringfellow. It's a really, really famous, highly cited paper that's meant to tell us a great deal about indium gallium nitride. And what it's showing us is that there's a solid line here, and everywhere above that, we'd expect the gallium nitride and the indium nitride in our indium gallium nitride quantum wells to be uniformly mixed, all just randomly scattered together. But below that solid line, we'd expect them to, the indium nitride and the gallium nitride, to split up into regions that have more indium in and regions that have less indium in. We'd expect those InGaN blotches that we were seeing in the TEM. Now, I'm just going to explain this a little bit more on where it comes from. So this is now a schematic phase diagram. I've just got an alloy of A and B, okay? At high temperature, above this solid line, I'd expect to have a single phase that I'm calling alpha. So all the material just randomly mixed together. And at lower temperature within the compositions defined by this solid line, I'd expect the mixture to split up into two phases. I'm calling them alpha 1 and alpha 2. That's because at the high temperature, the energy of the material, as it varies with composition, so this is now the Gibbs free energy of the material against composition, it varies with composition, but in a way that there's just one minimum. Whereas at a lower temperature, the Gibbs free energy versus composition curve varies differently. So we can see it has two minima and a maxima. So what this is saying is that for the phase alpha, having all the material just mixed up and being all randomly mixed together would have quite a high energy. But if we split up into these two separate phases, one with a lower composition than the average composition of the alloy, and one with a higher composition than the average composition of the alloy, we can lower the overall energy. We can split up into two low energy phases rather than having one high energy phase. Now, there's also this dotted line on the phase diagram. What is that telling us? Well, within this curve, which has this kind of cubic form with the two minima, there are 2 points where there are points of inflection, where d2g by dx squared, the double derivative of the energy with composition, is 0. And if we think about compositions that are between those 2 points, so like my composition x dashed here. Now, If my single phase alloy, my alpha, had composition X dash, it would have a high energy, okay? And it could get to a lower energy by splitting up into compositions X1 and X2. And that's really easy to achieve here, because if we start off with material at composition X dashed, and just by a little random fluctuation, we see it have a slight change to being material which is slightly more B-rich on the one side and slightly more A-rich on the other. So we begin that process of splitting up the material, which was all one uniform phase, into this phase-separated version. Well, we have a bit of material at this energy, a bit of material at this energy on this side. Let me put the pointer back on, which is where I've not got it. So a bit of material at each of these compositions and these energies. And that immediately lowers the energy. So for compositions that are between these 2 points of inflection, as soon as the material starts to decompose into the high A and high B regions, then that will lower the energy. And that's an easy process because you're lowering energy immediately as you start to make it happen. So this, these compositions defined by these points of inflection are defining what we call the spinode on the phase diagram. That's this dashed line. And within this dashed line, we expect decomposition of indium gallium nitride into indium rich and indium poor material to be not just energetically favorable, we also expect it to be fast, so kinetically favorable and likely to occur in the real world. Now, that line actually has the name of, given the spinode, but we sometimes call it the chemical spinode. And the chemical spinode is something that's quite easy to calculate, but it's not necessarily the complete real world picture. Because if we take a phase diagram with a chemical spinode and we take into account strain, we have to see how the phase diagram changes. And in general, if we take into account the fact that our A-rich material on the one side and our B-rich material on the other have different lattice constants, so that the interfaces between them, when the material splits up into the different phases, will be strained, that tends to provide an energy barrier to this decomposition. And that energy barrier prevents the decomposition and moves the spinode, therefore, downwards. This is what we call the coherence spinode, which is more realistic in the real world because it takes into account the impact of the strain energy. Now, people started to take into account the impact of strain in their calculations of the phase diagram for indium gallium nitride. Here's a version from Karpov, and then later a much more sophisticated calculation by Louis and Zunger, but both attempting to take into account the impact of strain on this phase diagram that was originally calculated. And comparing to the original Hohenstringfellow phase diagram, what we can see is that these things look very, very different. Now, I'm not going to get into the details, particularly of what's going on down here with the sophisticated Louis and Zunger phase diagram. The key thing you need to know is the indium gallium nitride in the blue LED used in your LED light bulb is round about 20-ish% indium and is grown at around sort of 700 to 750 degrees C. And if I mark that with my little blue LEDs on each of these phase diagrams, the Hohenstringfellow phase diagram predicts you will get decomposition, but the other two phase diagrams predict that you won't, okay? So a lot of the understanding of the early TEM data was based on the Hohenstringfellow predictions, but it doesn't take into account the fact that strain should suppress that decomposition into indium-rich and gallium-rich regions. Okay. So a metallurgist would go and look at the phase diagram. Great, well done, metallurgist. But really now we've got 3 different phase diagrams and we still don't know what's going on. Well, another thing a metallurgist might do to do an actual experiment is to do an experiment using atom probe tomography. Okay. So let's imagine we're a metallurgist for a second, and this is a metallic sample, a needle-shaped sample. Okay. And we're going to hold it at low temperature, sort of maybe 20 Kelvin, really quite low temperature, and a high DC bias. Now, this needle-shaped specimen should have a radius of maybe 100 nanometers, so a very, very sharp, pointy needle. So there's a really large electric field builds up around the apex of that needle. So we're going to take the needle to just below the threshold for field evaporation of ions from the apex. And then what we do is just kick the voltage up a little bit, add a voltage pulse. And when we add that voltage pulse, hopefully an ion will evaporate from the needle and will fly to a detector over here. And for each voltage pulse, we should get an ion evaporating, coming all the way to this detector. Now, this detector is sensitive to where the ions land. Okay? So each ion that lands should sort of create signal from the detector, which is sensitive to where the ion came from in X and Y. So that means we can track back to where the ion came from in X and Y on the needle. So that gives us the XY coordinate of the ion. If we want a three-dimensional picture, which we'd really like here, then we need to know the Z coordinate as well. And the Z coordinate is going to simply be found from the order with which the ions reach the detector. What we want to do is being very gentle with our voltage pulses, so that for each pulse we get on average, in fact, less than one ion, so that some pulses we don't get any ions at all, and sometimes we get one, and occasionally we get two, but we really try and avoid that. So that means in that case, we're evaporating the needle one ion at a time, and we can't evaporate the ions back here until the ones above them are gone. So the order of arrival at the detector tells us about the Z coordinate. The next thing this wants to be able to do for us is tell us what the ions are. And we're going to do that using time of flight mass spectrometry. Essentially, if we have the same accelerating voltage, a heavier ion is going to take longer to reach the position sensitive detector. So if we measure the time it takes for the ions to fly from the needle to the detector, that's going to tell us their mass. And because we know their mass, we'll be able to work out the composition of the material. So all in all, we've got the X, Y, and Z coordinate of each ion and the mass of that ion, and we can make a three-dimensional picture of the composition of the material. So this is an example of that from metallurgy. This is a stainless steel sample. And what we've got here is a sample with iron, chromium, copper in it. And we're showing up here in red regions that are essentially iron rich and regions that are chromium rich. And we've also got a tiny splodge there of copper rich material. And this allows us to look at these kind of nanometer scale variations in composition in metals. And we're interested in nanometer scale variations in composition in semiconductors, in indium gallium nitride. Now, the trouble is that indium gallium nitride is not very conductive, and it tends to be on a sapphire substrate, which is really not very conductive. So compared to a metal, it's much more difficult to apply a fast voltage pulse. So we have to adapt atom probe tomography to deal with semiconductors. And the adaptation we make is that we still hold it at a high DC bias, but rather than using these fast pulses to generate the field emission, instead, we just warm it up a tiny bit using a laser. And actually what we're doing is that rather than taking the voltage over the field emission threshold, instead we're moving the field emission threshold using the little pulse of high temperature from the laser. So we pulse a laser onto the tip, that causes the ion evaporation. And then apart from that, we can just do our atom probe tomography in the same way we would for metallic samples. The next problem we came across was that we then needed to make these incredibly sharp needles from our indium gallium nitride quantum wells. We needed an 100 nanometer diameter spike, which had our quantum wells right at its apex. And then it had to be a long spike so that we didn't end up with ion evaporation from other parts of the sample. And well, 1 to 2 microns, long in my world. And it also had to be connected to our voltage source. Otherwise, we wouldn't be able to apply our bias. So that gave us some problems when we first tried to do this type of microscopy, at a point when really this was a technique only really applied to metals. So our starting point here is a semiconductor wafer, a 2-inch wafer of gallium nitride on sapphire. And that gallium nitride may have fairly limited conductivity, And this is not something that's easy to make into a needle. The way we did that fabrication of the needle was using focused ion beam milling. We've got a beam of ions and we're going to sputter away into the sample using that beam of ions, which is very focused. We can also use it for imaging, like an SEM, like a scanning electron microscope. We can use it for deposition by introducing a platinum-containing precursor gas into the microscope. And we can also use it for machining. Now, making transmission electron microscopy samples in the focused ion beam microscope is a quite well-known technique. You start off with your sample, you put a strip of platinum on the top, and then you use your ion beam to dig some great big trenches on either side of your region of interest, and then you more gently with your ion beam thin down your membrane that's going to go into the transmission electron microscope. So you make this sort of wall of gallium nitride in our case with trenches either side. So going from that point, here is our membrane that is similar to a transmission electron microscopy sample. We've used the ion beam to cut down one side of it and along. So it's like a beam suspended in space here. We bring in a micromanipulator. This is basically just a needle. We use the ion beam and the precursor gas to deposit platinum. So the needle is attached to this foil. We chop the foil out and we can then take the rest of the wafer away. And there's our little foil suspended on one needle. And this second needle here is essentially our sample holder for the atom probe. We bring the membrane to the needle. We strap it on with platinum, like using a piece of sticky tape. And then we chop away the omniprobe. And we can strap our sample down really well with platinum at this point. So it's well connected to our needle, and that is going to give us our electrical connection. And then we start milling down our block of gallium nitride using annular milling. So basically donut-shaped, ring-shaped milling to create first a post and then our very, very narrow needle stripe structure. So this is actually one of our very first atom probe specimens. And this is what it looks like stuck on the top of a big steel needle. And from that, we can then actually collect an atom probe data set for this indium gallium nitride quantum well sample. This happens to be a green emitter rather than a blue emitter, but you can see the quantum wells here as the orange stripes with the blue gallium nitride material between them. In this image, in fact, each tiny dot is a single atom detected in our atom probe setup. And I'm showing all the indium atoms as orange dots. I'm only showing a quarter of the available gallium atoms, and they're the blue dots. And we're detecting the nitrogen atoms, but I'm not showing them because there's nitrogen everywhere, and it makes it really difficult to see what's going on with the indium and gallium if I show them in my data renders. Okay, so the picture's very nice. We can see the quantum wells, we can see the gallium nitride barriers between, and that doesn't allow us to say, have we got these high and low indium content regions? Because just like the TEM data, in fact, this is a projection because I'm just making a two-dimensional picture of a three-dimensional object. So we need to kind of think about what's happening with the compositional variations within these layers. And rather than doing that with our eyes, it's better to do that with some statistical analysis. So essentially here, I've cut up the quantum wells into little blocks, which are about 50 atoms in size each. And I've measured the composition of each of those blocks, okay? And what we're looking at is the frequency with which different compositions occur against the composition. Now, the crosses are our actual data, here for a blue emitting sample, a blue quantum well, and here for a green emitting sample. And the line is what we'd expect if the indium content of the quantum well is randomly distributed. So this is what we expect for the single phase case where there's no tendency to form blobs of indium, clusters of high indium content. Now, one thing to be aware of here is that even in the theoretical prediction, there will be some 50 atom regions that have a 40% or even a 50% indium content in a sample which has an average indium content of around 17%. And that's because alloys are random, they're not uniform. It's like if we were playing a game and I was throwing a dice. Sometimes if I throw the dice 10 times, I will get 10 sixes all in a row. It's not likely, it doesn't happen often, it's not a common event or a frequent event, but it's something that does occur. And just the same, if we randomly distribute our indium atoms, now and then we'll get a load of indium together, okay? So this curve is what we'd expect for the single phase region I was talking about on our phase diagram. And the data follows it really quite nicely for both the blue emitting and the green emitting material. So that suggested that these indium-rich clusters, these big blobs of high indium content, were not actually the key answer to why LEDs work so well. Atom probe wasn't finding the non-random clusters that we were expecting from the transmission electron microscopy data. So that became quite a controversial suggestion in the indium gallium nitride community, because people had really believed that those clusters were key to the devices working at all, okay? So people were very distrustful of our data, and they said, well, you've got this strange new technique called atom probe, which nobody uses on semiconductors. You're probably just not doing a good job and you're not finding the clusters. So we needed some clusters to show that we could find the clusters. So we put an atom probe sample in the transmission electron microscope, and we boshed it about for a while to create some clusters, to create that contrast, that blotchiness that you saw in the TEM data. So you can see here are our initial quantum wells, which are quite uniform. And here we are, we've put them in the TEM, and you can see they're becoming more blotchy due to the electron beam exposure. And we took that damaged sample that had been in the electron beam, and we looked at that in the atom probe. Now, the plots I'm showing here are the same as on the previous slide. I've got the frequency of a specific composition against the indium content, okay? And the control sample is one that hasn't been boshed about by the electron beam. And we can see that the data overlay each other quite nicely. And then I've taken the difference between the actual frequency seen in the experiment and the predicted frequency from my random alloy picture. And what you can see is that my difference plot looks very like random noise, okay? So there's no kind of clear trend in that there's lots of regions of high indium content or low indium content. But if we look at the damaged sample, that same difference plot is showing excess indium at the, excess regions at the low indium content end, excess regions at the high indium content end, and not enough regions with the typical indium content. So that's a signature that this is not a randomly distributed indium content. There is clustering, there are regions of high indium content. The probability of this distribution occurring randomly is about a half, so quite likely. The probability of this distribution occurring if we've got a random alloy in our indium gallium nitride is less than 0.001. So this is very, very unlikely to be a random sample. It really does have indium clusters, but they've been created by the electron beam. Even when we showed that, people still didn't believe us that the atom probe could find these clusters. They wanted to see as grown clusters that were in the original indium gallium nitride material. Now, that turns out to be quite difficult to achieve in blue quantum wells that are grown on the polar C plane of gallium nitride. So the gallium nitride crystal is hexagonal, and the hexagonal crystal has different planes within its crystal structure. And normally we grow, if we imagine the hexagonal crystal as a hexagonal prism, we grow on this top face, which we call the C plane. That's where we put our quantum wells, okay? But we can also put our quantum wells on other places. So here we're putting them on a plane called the A plane, which is a sort of squarish plane that I am highlighting as a purple rectangle. So we grew samples like that, and we looked at them in the atom probe. And again, so here my indium is pink and my gallium is yellow, but the same kind of thing, we can pick out the quantum wells. And if we look down on them from above, we start saying, does that look a bit blotchy? In fact, when one of my postdocs came to me with this data, he said, I found clusters, Rachel. And I was like, no, you haven't. We don't pick out these clusters with our eyes. We do the statistics. I bet it'll turn out to be random. I was wrong. I often am. Because when we did the statistical analysis and looked at the frequency difference plots, again, we could find that there were regions, lots of regions with too little indium content, lots of regions with too much indium content. And again, these A-plane quantum wells we could show were very, very unlikely to form randomly, that there were real clusters, which in this case we could also pick out nicely with our eyes in the data. We did the same thing for another plane. This is the M plane, the side of my hexagonal prism. And we found exactly the same thing. Too much indium, too many regions at low indium content, too many regions at high indium content, not enough in the middle, a statistically unlikely distribution for a random alloy. So we can make indium clustered material. We can detect indium clustered material. But the normal material, grown on the C plane, which is the material that is in almost every LED light bulb that has ever been sold commercially, that is a random alloy. Okay, so we started off with a picture where there were defects through our quantum wells, and those defects would cause non-radiative recombination of carriers and spoil the performance of the device. We then said there has to be something going on with the microstructure which stops that. And it could be indium content variation, so these high indium splotches which would localize the electron and hole and prevent them from moving to the defect site. But we've shown that in blue LED materials, they're not there, at least not in the ones that are used commercially. But we've still got this question of the well width variations left. So let's see whether we can find any well width variations in the data, whether the quantum wells have regions that are thicker and thinner. Well, here is a couple of data sets from quantum wells. This one's the atom probe, and this one is a completely different sample, but it's TEM. And if we look at our quantum well, what we're showing here are iso concentration surfaces. So they are contour maps of points on the quantum well that have the same composition. So like iso bars join points of the same pressure in a weather map, iso concentration surfaces join points of the same concentration in an APT dataset. And we've pulled out here the bottom interface of the quantum well, where the InGaN was grown on gallium nitride, and the top interface of the quantum well, where the gallium nitride was grown on the InGaN. And what we can see is that the bottom interface is very smooth, but the top interface is very bumpy. The height of these bumps is only 1 or 2 monolayers of indium gallium nitride, but they're all over the place. And in fact, if we look at the TEM, we can see that in the TEM, there's just the same thing going on. The bottom interface is very smooth, and the top interface is much more ragged. We've actually seen the same thing using some specially designed atomic force microscopy experiments. We've seen it using X-ray diffraction, that there's differences in roughness between the top and the bottom interfaces. So overall, there's a good body of evidence that the well width fluctuations exist because of this top surface roughness that we can see. Now, here we start to get into really some detail about what happens to electrons and holes in these quantum wells, which are random alloys and which have these well width fluctuations. So these are calculations from my colleague, Stefan Schultz at the Tyndall National Labs in Ireland. And he's using atomistic calculations to identify where the electron and hole will end up. So in his model, he has every atom of the indium gallium nitride crystal structure, and he generates random configurations. So it's a random alloy within his model, the indium gallium nitride. And the first thing we can see, so this is the quantum well seen in cross section, flat bottom surface, roughness shown just as a monolayer island on the top surface. Looking down on the same model from above, we see our monolayer island as this circle here, okay? So that's his simplified model of what we see in the microscopes. We can also see we've got red and green regions. The red regions are telling us about where the electron is, and the green regions are telling us about where the hole is when we put them into this quantum well system. Now, the electron is tending to localize at this well width fluctuation that we have seen in the data, but the hole is localizing somewhere else. The electron and hole are pulled apart here because indium gallium nitride is piezoelectric, there are internal electric fields across the quantum well which separate the carriers to opposite sides of the quantum well. So here's the hole down at the bottom interface of the quantum well, and we've got different configurations. There's many different configurations in the paper, but we've got configurations 1, 5, and 8 here. And we can see that the hole is in various different locations in those different random configurations that the different models contain. And if we then go look very carefully at what's going on, it turns out that just at random, these are regions that happen to have a few more indium atoms. So as I say, there's hundreds of atoms in this simulation, and occasionally if you throw a dice 3 times, say, you'll get 3 6s. And here you've ended up with maybe 2 or 3 indium atoms that happen to be in a chain, one next to another. And that tiny, randomly occurring fluctuation in the indium content is enough to localize the hole. Now, if we look at that overall, we've got both the electron and the hole trapped. They're trapped, in fact, separately from one another, which will have real consequences for the optical properties of the material. And in one case, there actually is a trapping at a compositional fluctuation, but it's not like a big cluster of indium, like the original suggestion. It's just a tiny little local random fluctuation in the indium. But together, the step and the little cluster of indium are enough to trap both the electron and the hole. So neither of them are going to be moving to a defect, to a dislocation, which might ruin the properties of the device. So our electron and hole are trapped separately, but neither of them can reach the defect. Okay, so we now have a picture of why our blue nitride LEDs work, even though they're full of defects. So what else are we researching? We know what's going on now. Well, obviously, there's a huge amount we can still do to improve the performance of these devices. And just in my last couple of minutes, I'm going to introduce you to one of the big live problems in the field. And that's the problem of droop. Now, what is droop? Droop is the fact that as we drive an LED harder, as we run more current through it, its efficiency decreases, okay? And that's a problem because in order to light up a room, we need quite a lot of light. And what we want to be able to do is drive the LEDs hard and make them emit really brightly. But when we do that, we get less and less efficiency in the device. So we're making more and more heat and wasting more and more energy. So what's going on? Well, if we make a curve of the efficiency against the drive current here on a log scale, in fact, as current density, we see low efficiencies at the lowest currents. At moderate currents, we see really quite high efficiencies. And at the highest currents, the efficiency drops off again. Now, what's going on at the low current end is that we do have some non-radiative recombination at defects, and that is tending to dominate the low current end of the curve. As we put in more carriers, though, we see the radiative recombination start to take over. The question is, what's happening at this high current end? And there are lots of different suggestions for the answer to that question in the literature. It might be Auger recombination, it might be carrier leakage, it might be the effect of the defects being different at the higher current densities. Now, we're going to look at this not using the microscopy techniques I've mentioned up till now, but using optical techniques. These data I'm showing here are from photoluminescence, so we're exciting light emission from the quantum well with a laser. And we're looking at how the energy of that emission, so the color of the light, the energy of the light that's emitted from the quantum wells changes as we increase the temperature. So what I've got as 0 here is the color that we start with at very low temperature. We're kind of calling our 0 point, and we're saying, okay, does the wavelength increase or decrease with temperature? And what we see is that there's an initial red shift in the energy, and initial drop to lower energy, so a redshift of the wavelength, and that after that it decreases again. And this is referred to as an S-shaped temperature dependence because it looks a bit like an S if you squint. Okay, so what's going on? Well, this is a signature of carrier localization. So we have these electrons here in the quantum well, and I'm drawing the different regions of the quantum well, which have different energies because of their different both indium content and well thickness, just as these lines here. And there's lots of different localization sites relating to different configurations of the indium content, different sizes of well width fluctuation, all with subtly different energies. And at low temperature, we inject carriers in and they find their way to a state, and then they're stuck there because there's no thermal energy at the lowest temperatures to get them out of these states and into any of the other states. But if we increase the temperature a bit, there's enough energy to move the carriers out of the states in which they're initially stuck and allow them to diffuse to lower lying states. So we get a redshift because they all move down to lower energies. Okay? If we then continue to heat up the sample from about 50 or 60 Kelvin here up towards room temperature, there is some random thermal redistribution. So some carriers end up in higher lying states. So we see the energy of the emission shift back towards the blue. So whatever the localization states are, we can detect them optically using this S-shaped temperature dependence of the peak energy. If we then look at what happens to that S shape when we increase the excitation density, so as if we were turning up the current in the LED, but here we're just turning up the laser power we're using to excite the carriers, we see that that S shape vanishes. So this looks like the carriers aren't localized anymore, but the laser being a brighter intensity at a higher excitation power can't remove those localization sites we've identified in the microscope. So at low power, we've got this redistribution of carriers among the localized states that we've already discussed. But at high power, we don't see it, not because the localized states are gone, but because we've filled them all up. There's no spaces left in the localized states. And if we keep adding more and more carriers, they may end up in the quantum well, but they won't end up in those low energy sites. So if we've saturated the localized states, that may well mean that the carriers can now move through the quantum well, no longer trapped by those high indium content regions. They can reach the defects and they can recombine non-radiatively. Now that's just one of the concepts being used to explain the droop problem. It may be that the carriers, that we saturate the localization states and that we see the carriers recombining non-radiatively, but it's not actually due to the dislocations. It might be, for example, there is Auger recombination, but the Auger recombination is affected by the saturation of the localized states. So it's not necessarily entirely unpacked, the relationship between the localization and the droop. But I think it's very important that we always remember what the real structure of these quantum wells is, and the fact that that will affect very, very strongly how the carriers move and recombine when interpreting these phenomena and designing how we make better quantum wells for better LEDs. But this remains quite a controversy in my field. Okay, so let's sum up. We've been talking about the material science of blue LEDs, and I said, start with that these materials are full of defects, dislocations, which we'd expect to wreck their properties. In order to understand the microstructure of the quantum wells and what it is about the indium gallium nitride quantum wells that prevents these problems with the dislocations from ruining the performance of the device, we used atom probe tomography. And that atom probe tomography showed that the quantum wells are actually a random alloy. Nonetheless, because of the effects of the random localization centers which appear just because sometimes you do get a few indium atoms at random close together, and because of other microstructure, the thickness fluctuations in the quantum wells, we do see strong localization of both the electron and the hole. And that is what is enabling these highly defected materials to be successful performers in the LED light bulbs, which are revolutionizing lighting and making it much, much more environmentally friendly. So I hope you've seen the link there from the metallurgy, where the early subject learning about the structure of materials right down at the atomic scale, through to the materials like our semiconductors. For all these things, we look at the structure of materials and how it links to their properties. For the LED, the structures that we've discovered are random alloy fluctuations, not major clustering, and also well width fluctuations, controlling the ability of carriers to diffuse and hence the efficiency of those materials as light emitters. We might choose to change the processing to make more of those recombination sensors to try and improve the performance. And that relationship between processing, performance, properties, and structure is the heart of material science, and I believe is key to optimizing optoelectronic devices in many cases. Thank you very much for listening. It's been really great speaking to you, and I'm really happy to take questions. So, any questions?
Thank you for the enlightening session, ma'am. We have got an opportunity to explore more on Indian gallium nitride light emitting diodes, and we really enjoy the session. And now it's a time to get all your doubts clarified. The participants, please come up with questions and make the session interactive and more informative. Thank you. So come up with your doubts.
Good evening, ma'am.
Evening.
We really enjoy your section, and we willing to know that upcoming evolutions on LED, ma'am.
I'm really sorry, I'm not hearing all that well. Would somebody be willing to type the questions in the chat for me so I make sure I capture them? Is that possible?
Upcoming evolutions of LEDs.
Upcoming evolutions of LEDs. Okay, did I get that right? Yeah. So the thing that I'm most interested in at the moment in terms of new directions for LEDs is actually using indium gallium nitride for longer wavelength emitters. So traditionally, indium gallium nitride has been the material of the blue LED and the green LED, and we've used indium gallium phosphide for the red LED. And the indium gallium phosphide devices are very successful, and I don't think we felt we needed indium gallium nitride in the red. These days, people are more and more interested in micro LEDs for displays, particularly for things like the Apple Watch, but then for even smaller displays, like for augmented reality or virtual reality. So LEDs at the maybe 10 micron pixel level. And it turns out that indium gallium phosphide isn't necessarily going to be the best material for that, because a micro LED has a lot of edge per unit area. And all that edge is a problem because in indium gallium phosphide, you get a lot of surface recombination. Carriers very easily diffuse to surfaces and recombine non-radiatively. So small indium gallium phosphide LEDs turn out not to be really efficient. So it's one of the exciting things for me is looking at ways to make red LEDs in indium gallium nitride, which historically has been a really, really difficult problem. And we're finding new ways to do that now. And I think that's one of the exciting new directions in LEDs that I'm most interested in at the moment.
Thank you, ma'am.
Thank you.
Any questions? Hello, ma'am. This is Sivarita.
Hello.
Actually, I'm really interested in nanotechnology, ma'am. So, can you please add some words on that? Where to start my career in that field?
How to start a career in nanotechnology. So I think, so nanotechnology has come to a lot of different things. Yeah. So if you look at some of the nanotechnology journals, they're defining nano now as everything below 500 millimeters, which encompasses a huge amount of things. I'm most interested in the in nanotechnology where we're talking about the sub 100 nanometer length scale. And I think then the key things is understanding why at that length scale nano is different. So I'm always really interested in the kind of quantum effects that we see in that very small length regime. And it's where we exploit those differences at the nanoscale from quantum effects and other nanoscale effects that can't be achieved in the macroscopic materials that I think nanotechnology is at its most interesting. Also, from a personal point of view, because I'm really interested in materials characterization, I think it's very important to develop the techniques that allow us to properly characterize the nanoscale. Because if we can't measure the structures of these nanomaterials properly and in sufficient detail, we can't really understand them. So I think learning about the quantum aspects and the characterization aspects are both quite separate things that are exciting for nanotechnology, but really important.
Thank you, ma'am.
No, came off.
Good evening, ma'am.
Evening.
This is Jay Shakti. There is gallium arsenide has a life scale of less than 100 hours, and then gallium nitride has about 1 lakh hours, I think. Is there any element which is in research which has more lifetime than gallium nitride, ma'am?
Sorry, I didn't quite catch that. Could you do it once more slower?
Is there an element like gallium nitride?
Oh, now I can't hear at all.
It has. Is there an element which is in research which has life hours more than gallium nitride?
Sorry, I'm not getting anything. The internet's gone really unstable. Give me a second. I'll try switching my connection. Okay, can you hear me at all now?
Is it audible now?
Can you hear me?
Yeah.
Okay, I can hear you again. So, sorry, try one more time. I didn't hear anything the second time at all. You froze completely here.
Is there any element which is in research like gallium nitride, but which has a life hours more than gallium nitride, ma'am?
That has a lifetime more, a longer lifetime.
Sorry, ma'am?
So did you say, is it a material which has a longer lifetime than gallium nitride?
Yes.
Yeah, ma'am.
So I don't really know. So in terms of the device lifetimes, you mean? Do you mean in terms of the device lifetimes?
Yeah.
Yeah. I'm not sure once you get the devices above the sort of 50 to 100,000 hour lifetime, people really check. Because at that point, in practice, the LED bulb that is going to go into your house, if you install it now and the only thing you have to worry about is the failure of the LED, it will probably live longer than you do, even though you are younger than me. Okay, so these are very, very long-lived devices, and it becomes almost irrelevant whether once you're up to 100,000 hour lifetimes, given how often they're actually used, it becomes not really a question that anybody needs to worry about all that much. The thing I would say is that if you actually do install LED light bulbs in your home, you may find they fail a lot more quickly than that. And it's not because the LEDs themselves are failing. The LEDs themselves are intact and beautiful within that light bulb, okay? The things that fail are the electronics that drive them. So they need AC to DC conversion to work successfully, and the drive circuits for that tend to fail. And sometimes simply the connection, so the wire bonding or the connection between the LED and the rest of the system fails. So the LED can be sat like in the bulb, absolutely functional, but with no way to apply a voltage to it because the electrical connection is broken. So in many ways, the device lifetimes, in terms of the practical applications, the device lifetimes aren't really the big issue. The issue is how we build the system around the device to ensure that the whole thing works really well.
Thank you, sir.
Yeah, thank you. I got it.
Thank you. I'm sorry it took me a long time to get the question.
Yes, ma'am. Turn that mic off.
Hi, ma'am. You said that LED has many benefits, but why do you think it's not most famously used in all over the world? And still, people are using incandescent bulbs and all those which promote more global warming and stuff. So why is LED not more famously used?
So I think one reason for that is cost. So in fact, if you kind of look across the lifetime of an LED, it will save you lots of money, okay? Because the energy cost of running the LED bulb is really low. And assuming that you've got a good LED bulb when the drive circuits don't fail, that bulb will last you a very long time. So if you look across the full lifetime of the LED, the cost savings are huge. But your average person doesn't necessarily think, right, okay, across the 100,000 hour lifetime of this bulb, how many filament bulbs would I need to buy? What is the saving of my electricity bill? They think, how much money have I got in my pocket today? I need a new light bulb. I'll buy the cheap one. Yeah, and that's fair enough, because if that's how much money you have got in your pocket today and you can't afford the expensive one, the long-term cost savings are no good to you. Yeah. So LED bulbs remain much more expensive than conventional bulbs. We're working to bring those costs down. Some of the work done in my group is about using cheaper substrates. So the sapphire substrates I talked about are really quite expensive. Silicon substrates are a lot cheaper. So we make LEDs on silicon, and that helps bring the costs down. But actually the cost of the whole package, the bulb, the actual LED chip is only a tiny fraction of that. And again, it's the drive circuitry, it's the things to cool the LED and make sure it stays at the right temperature, it's the packaging. All of those costs have to be addressed to make them cheap enough that like everybody can go out and buy them, even if they've not got much money in their pocket. And then they'll come into much more common use, we hope.
Thank you, ma'am.
Thank you.
Thank you for the informative session, ma'am. Now, as a token of honor and gratitude, I request Dr. S. Brinda Student Branch Counselor, to present the memento.
Ma'am, kindly accept this memento, ma'am. Please.
Thank you very much.
Thank you, ma'am, for the wonderful presentation and interaction with the students. Thank you very much. On behalf of IEEE Student Branch, Sairam Engineering College.
Thank you very much for listening.
We will meet you in, with some other program very soon.
Sorry, I didn't. I'm still not hearing very well.
Conference. Actually, we are planning to organize international conference during the month of March 10th and 11th. We are willing to invite you as a keynote speaker, ma'am, for the conference.
It sounds lovely. I can't quite catch when it is, so maybe if you could write me an email and we could discuss. That sounds interesting.
Thank you, ma'am.
Thank you very much. Bye-bye for now. Bye-bye.
Bye.
Now, may I call upon Suvandhini S. to deliver the order of thanks. Arjun, it's a great honor and privilege to support the board of tax occasion. First of all, start with Almighty God for making today's occasion a resounding success. First and foremost, I thank our chief guest, Dr. Basil A. Oliver, Professor of Material Science, University of Cambridge, who, despite a busy schedule, has found time to grace the occasion. Thank you, ma'am. And I express heartfelt thanks to the CEO, Sri Sairam, and Principal Dr. A. Rajendra Prasad, Dr. K. Photoluminescence Director of Sri Sairam Institution, Dr. C. R. Remy Robbins for valuable support to this occasion. I would like to extend my thanks to our DEPT SD Counselor, Dr. S. Brinda, for giving us full support to organize their function. I wish to thank society members S. Aditya, G. Shweta, G. Vinita, and G. Pooja, who work hard to ensure that this occasion becomes a friendly success. Last but not least, I wish to thank staff and friends for the cooperation in making the function a grand success. Once again, I thank you for your